Welcome to 11.7 Sequences and Series as Mathematical Models. Since a sequence is a function whose domain is the set of integers, the graph of a sequence changes by jumps rather than a smooth, continuous curve. Therefore, sequences are appropriate as mathematical models for real-world phenomena in which the dependent variable changes stepwise rather than continuously. For example, when you hammer a nail into a board, the distance the nail has traveled is a stepwise function of the number of times you hit it with the hammer. So today's goal is that given a real-world situation, we use a geometric or arithmetic sequence/series to model it. Let's take a look at example 1. You start a walking program with a basic walk of 8 miles per week. Each week you increase your distance by 10% of the amount of the week before. What is the distance you walk in the 8th week? So if we look at this and we think about, we're increasing 10% of the original amount. So we're not really adding 10%, we're multiplying by 10%. So to the previous number, we're using 100% of the previous number plus another 10%, so we can multiply by 1.1. So if we think about, we're looking for the 8th week. That could be our t sub 8. Our initial amount was 8 miles. That's t sub 1. We know that our multiplier, our common ratio, would be 1.1. And then if we do to the n minus 1, this would be 8 minus 1. So we have 8 times 1.1 to the 7th power, which gives us 15.6 miles. So we know it's geometric. What is the total distance? Well, another word for total would be the sum. So the total distance in 8 weeks is the sum of 8 weeks. So the first term, t1, was 8. And then remember the formula from the previous days. 1 minus r, well r is 1.1, to the n, which is 8, all over 1 minus r. I would just do this right in your calculator all at once, and you're going to get approximately 91.5 miles. That's a lot of miles. Let's move on to example 2. A car depreciates in value each month that you own it. This is an interesting word, but it's a very important word as you move through life, because as you buy cars, hopefully all of you will have a car someday, maybe, and maybe you'll live in a city where you don't need a car, but most of you, I would gather, that will have a car. Your car is going to lose money from the day that you buy it to the day that you sell it or trade it off, etc. It's going to lose money. So let's assume that you start off and you paid $15,000 for a new car. Now when I say new, I mean probably used car, but a new car to you. And you bought it on September 5th, 2019, just last year. The value of the car depreciates by 0.001 of its original value each month. So what's the value on October 5th, 2019? So that's just 1 month. So essentially that's T2. The original number was 15,000, and we're multiplying by 0.999 times 2 minus 1, because it's just 0.99 of the original. That comes out to be $14,985. What's its value 1 year after purchase? So 1 year is 12 months. So we have to think about, we started with, oops, sorry about that. So we have 15,000 times r to the 12 minus 1. That's going to be equal to 14,820.99. What is the value of when the 6-year warranty expires? So the 6-year warranty is 72 months. So your warranty ends, after it starts basically the day you buy the car. So the 72nd month, you started with 15,000. You're doing 0.99 of 72 minus 1. So T of 72 equals 13,957.46. So when will the car be worth nothing? So 0 is equal to 15,000 times 0.99 to the n minus 1. So when is that going to be? Well, if you were solving that, you divide by 15,000. You get 0 equals 0.999 to the n minus 1. So think about the powers of 0.999. 0.99 to any power is never going to yield 0 for an answer. So this has no solution. So the answer to the car is it's never going to be worth nothing. It's always going to be worth at least some little value. Example 3. A water well costs $4.50 for the first foot and increases in cost by 50 cents for each additional foot thereafter. Part A, what is the cost of the 50th foot in the water well? Well, let's think about this. We want the 50th foot. We're starting off with $4.50 for the first foot. That's T1. We're going to add 50 cents each time. So rather than doing a percentage, we're just adding a designated amount. So that's a common difference. So if we use our arithmetic sequence formula, we can use 50 for the nth term. We can use 50 cents for the common difference. We can use $4.50 for T sub 1. And we can calculate that T sub 50 is going to equal $29. What's the cost for the 80th foot? The 80th foot would be similar. You have $4.50. 50 cents is the common difference, but now you're doing 80 for the nth term. And that's going to yield the 80th foot is $44. What's the total cost of a 100-foot well? So now we don't want just the 100 foot, we want the total cost, digging it all the way down, layer 1, layer 2, layer 3, etc., all the way to layer 100. So we're going to do the sum of 100 terms. So arithmetic sum formula, 100 times 450 plus T100 all over 2. Well, we don't have T100, so we could find T100. Remember that alternate formula I told you about the other day? You could just basically go with the 450 plus 50 cents times 99 because 100 minus 1. So basically, if we think about this part right here is the nth formula. So it's the 100th term formula to find the term. And then back to our original, this whole thing would be over 2. So what that amounts to is you have the 100 terms. So n is 100. We said 450 was the initial. T100 ends up being 54. And then we can divide by 2 for a grand total of 2925. So 2,925. The other thing I guess you could have done also, if you think about it, is you could have used sigma notation, and you would have said, hey, I want to add up all the terms from n to 100 for the formula 450 plus 50 cents times n minus 100. That too would work for summarizing and the summation for 100 foot of well. Good luck on your homework.